Hey programmers, welcome back to day 11 of the Advent of Code. So let's start as always by looking at the input file for today. It's going to look something like this. And so what this represents is really like the map of the seating chart of an airplane. And so we can interpret each of these symbols in a special kind of way. So we'll say that the hashes are going to represent seats that are full, so they're taken. L is going to represent an open seat, and a dot is going to represent the floor. Let's start to visualize this one by interpreting every character as a position of some grid. So I can kind of reimagine things sort of like this. So I have my nice full grid. And I'm going to put these same characters at their respective positions on this nice and clean grid. And so to make our illustrations more clear, I think it would be better if we can use some colors to actually encode these different characters. So what we'll say is that the hashes, or the full seats, are represented by this reddish color. So I'm going to substitute all of these guys. In a similar way, we'll use green for all of the open seats, or the L's. So we'll plug those in. And finally, for the floor or the periods, what we'll do is just keep them as white. So far I have a structure that looks like this. And keep in mind the mapping that we have. All right, and so what we want to do in this one is figure out how the seating evolves over time. And to do that, we're going to have to realize what our adjacent sort of neighbors are at any point in the grid. So let's say I was situated at this yellow dot right now. I can consider my neighboring positions as just the 8 immediate positions next to me. So it'd be everything in this shaded region, right? So I can look diagonally as well as up, down, and left and right. And so at any point in time, if I'm at a position that's actually, on the inside of the board, then I can look at 8 neighbors, right? And so with that, we're going to have 2 rules to actually decide how we can change a position of our floor plan. So here's our first rule. An open seat becomes full if there are 0 full seats around it. So do keep in mind that we're using green to represent open seats and red to represent the full seats. So that's one rule. And our second rule says if we have a full seat, it can become open if there are greater than or equal to 4 full seats around it, right? So these 2 rules give us the criteria for flipping a green to a red and a red to a green. So before we see how this grid evolves over time, let's practice doing one manipulation. Let's say I was situated at this yellow dot, right? So I want to figure out for this position that I have covered with the yellow dot, how should it actually change? Well, which rule is this going to satisfy? Well, right now it's a red, so right now it's a full seat, so I should check if it satisfies rule 2, right? So this can become green if there are greater than or equal to 4 full seats around it. And there are more than 4 full seats around it. If I do a quick tally, I see 5 red boxes, and that means 5 full seats, right? 5 is greater than or equal to 4, so that means that this position should actually flip to a green. And we'd want to perform a similar inspection on every position of this grid simultaneously to figure out what our next grid looks like. So here's generation 0. I flipped it back to the original one. And let's say I applied these 2 rules to all of the positions simultaneously, right? That would give me a grid with possibly a different coloring. So I'm going to do that right now. Notice how the colors change. I have a lot more green in this one. So that was after one iteration, and I can iterate once more, resulting in this. And now we reach a very interesting point. It is the case that none of these positions on the grid, that is all of them, satisfy either of our 2 rules. So there are actually no further changes from here. In other words, we can consider this new grid as stable, right? It's not going to change any further. And so here's our overarching question for part 1. What we have to do is figure out how many full seats, or in our picture, how many red seats are left once things stabilize, right? So you want to keep kind of simulating those 2 rules until it converges to a stable state. And in this particular example, if you counted up all of our red seats, that would give us an answer of 37. However, for our actual puzzle input, it's going to be a much larger grid and probably give us a larger number of full seats overall. That being said, this doesn't seem too hard to implement. I think let's jump right in. Really, the difficulty is going to be about building all of this code. So here's our full text file. It's pretty large. Let's start in our part 1 file, and I'll just read the lines of that file, and then we'll just go ahead and just console.log what that looks like so far. It's going to be definitely a ton of lines. So something that I kind of want to establish in our code is it would be nice if we actually had some grid-like structure that we can access. And so here's what we'll do. Why don't we create just a very small input file for ourselves, because this output's just too large for me to even make some assumptions about. So we'll call this, I don't know, example. I'll create like a very, very simple grid, maybe just a 3 by 3, right? So we'll just do a bunch of open seats, and then maybe, I don't know, 2 pieces of floor. over here. So let me just read this file for now, just to make sure I get all my parsing down, right? Cool, so there's my grid. Let's also be sure to not put an empty new line in this kind of test file. Cool, so that's better. And what I want to do in the long run is make sure I can like mutate some data. So I'm going to actually turn the inner elements of this into an array, because I can't mutate strings in JavaScript. So maybe what I'll do is I'll say lines.map. And for every line over there, I can just do line.split. So I'm splitting one of these strings on the empty string. So that'll give me an array, and so I have a 2D array right now. I can maybe call that my const, we'll say grid. See how that looks. Print out my grid as well. Nice. A cool trick you can use if ever you have like a 2D array in JavaScript and you print one out, you can also do console.table, which is nice when it's just some simple character data inside. Now I can really see how that grid actually looks like, right? And also see the rows and columns, right? All right, so let's do some planning. I know that in the long run, what I have to do is target some position and look at its 8 adjacent neighbors, which in itself isn't difficult. It's just maybe a lot of writing. But what I also have to watch out for is what happens when I'm on like the border around the grid. Imagine I'm at this corner position, then I shouldn't really look out of bounds, right? There's nothing to my left, nothing below me, and also nothing in my sort of bottom diagonal in this direction. So we could do a lot of conditional logic to sort of guard against that, because I know when I kind of index or try to access a property on like undefined, it's not going to work out too well. So what I'll prefer to do is they give us this kind of like dot character, which represents basically nothing, just means the floor. So it's definitely not a seat. It's not an occupied seat. It's also not an available seat. So we can effectively ignore the dots. But they do take up space on our grid. So what I can do is actually just create a dot border around the entire grid, basically adding 2 rows on the top and bottom, and also 2 columns, 1 column on the very left and 1 column on the far right. That way, whenever I have like a corner case, it never actually looks out of bounds. It'd be technically looking into my dot border. So establishing that isn't too difficult. Let's say I wanted to add the top row and bottom row of dots. So I can create maybe a, we'll say, floor row, because remember that in the context of the problem, they say dots represent the floor. And what I'll do is I'll make an array of a certain size. It should be just the width of my grid. So I can say of grid index 0 dot length. So that gives me the inner length of the grid, or the width. And I want to create an array of that size and fill it up with a bunch of dots, right? Cool. And then from there, I'll create my maybe like let bordered grid. And I can take my original grid and copy it over. But after I take all of the rows from my original grid, I'm going to add my floor row before that stuff and also after that stuff, right? And I can print out my bordered grid. So this has the effect of putting a bunch of dots, or a row of dots, at the very top and also at the very bottom, giving me at least my horizontal borders, right? So just like this. Cool. And now doing the vertical border on the left and right is a little more complex, because I have to actually bake them into the inner subarrays, right? So maybe for line 10 over here, we'll kind of adjust this code a little bit. So instead of just taking the original line and splitting it, I'll also put some stuff around it. So if I do this, I'd be splitting all of the elements in the current line, but after them I want to put exactly 1 dot, and before them I also want to put exactly 1 dot. So just like this, kind of sandwiching my elements within a row with a dot on their left and a dot on their right, and that happens for every row. So this now should give me my full bordered grid, right? So let's run that. So I didn't save the file, let's run that again. Cool, and there I have it, right? I basically just put a nice border around it. So that's looking pretty good. Maybe I'll rename this variable. I'll say like I'll say bordered grid over here. And I'll just change this variable name as well to bordered grid. Nice. And now I think we're ready to actually tackle our core algorithm. All right, so here's what we'll do. Let's build a function that exactly performs one generation of our grid. So it should take in some grid and give back, we'll say, a new grid array. So we'll create that function over here. I'll call it, I don't know, next generation. It's going to take in some grid. And I don't want it to actually mutate the grid. What I'd rather it do is just return to me a brand new grid, right? So we'll prefer to do it like that. So we know that from one instance of a grid to the next, we'd just be doing some manipulations on it based on those two rules we spoke about, which are all about adjacencies. Something that I'll do is I'll do const, I'll say my new grid. And if I just do new grid equals grid, then technically both variables refer to the same array object in memory. So I don't want to do that, right? I want two distinct arrays because I don't want to get any weird pass by reference mutation behavior, right? So I'll create a quick function to just copy a 2D array. So I can say const, I'll say copy 2D, takes in some, we'll say grid, and what it can do is just maybe return grid.map, right? So map I know gives me a new array, so this is good so far. And I want to make sure I also copy over the inner rows of that grid, original grid. So I can say row, we'll just create a new literal array. So I already get some new array over here. And then I'll unpack the elements of the row. So all this does, if you're following along in another language, copies over a 2D array into a new array, right? So it's not going to be the same memory location. Cool. So now that I have copy 2D, I'm going to copy my original grid over here. And now I actually need to perform my code of iterating through every position of my original grid and checking if I need to update it, right? So let's lay down that logic. It's definitely going to be nested loops. So I want to make sure that I only iterate through the true positions of my grid. So that would mean stuff that is not on the border that I kind of added to the input, right? So technically I won't start at I equals 0. Instead I'll start at I equals 1, right? And then I'll iterate while I is less than grid.length. And of course, we'll just increase, right? I plus equals 1. In a similar way, I'll have my j's. And j's should also start at 1, I believe, for the same reason. In other words, in the very first iteration of this nested loop, I would be looking at position 1, 1 right here, which is perfect. I don't want to look at the border, right? Because I kind of just added that in. Nice. And so at this point, I know my current position. So I'll say const, we'll say center, maybe. So our current center would be the grid at position I, j. Nice. And then from here, I want to consider all of its neighbors, right? So there are a few different patterns that we can use for that. Let's say I just wanted to reference maybe my up neighbor. Well, it'll just be grid of I minus 1, j, right? And maybe my down neighbor would be I plus 1, j. Now I'd really write a bunch of different expressions like this to give me all 8 of my adjacent neighbors, right? For things that are diagonal, let's say I wanted to look at my down right neighbor, so diagonally to the right, then it would just be I plus 1, j plus 1. So let me write an expression for each of my 8 neighbors. So this will access all 8 of my neighbors, and I already know that these neighbors definitely exist because I got rid of those border cases, right, by adding my own border of dots. And so what I really want to do is check, how many of my neighbors are occupied. So in the context of my actual problem and my input right now, if something is occupied, then it's going to render as a hash, right, a hashtag. So let me check if each of these is a hashtag. So really just some conditional logic. What I want to do is something like this. Select all of these lines. And I know that this expression gives me a character. I want to check if that character is equal to a hashtag, right? And I know I want to just basically take a count of how many things are equal to a hashtag. So I'm going to make all of these elements of an array, right? So I'll call it const, I'll say occupied neighbors. And we'll save all of these elements into this array. So what we're already doing is putting some booleans inside of this array, which is actually, I think, good to go, right? So if let's say my down neighbor is indeed occupied, then I'll have a true for them. If they're not occupied, then I'll have a false for them. That means that in the long run, if I want to figure out how many neighbors are around me and are occupied, then I would just go ahead and take account of the number of trues within this, right? Within this array. So we can do that pretty easily. We can go ahead and get a const, we'll say occupied neighbor count. We'll say num occupied, which is maybe better here. Have num occupied, I'll set it equal to 0. And I'll just do some classic, iterations. So I'll say for, I'll say let val in occupied, or val of occupied neighbor. So I'm iterating through every element of this Boolean array. So val is always Boolean. What I want to do is just check, hey, if val is equal to true, then that's a neighbor that's occupied. So I should increment my num occupied variable, right? So plus equals 1 over here. So iterating through every element of that Boolean array, if the value is true, increment, right? And then at this point, I have my nice count. So I can perform my overall logic, right? So recall that in the problem, we want to check, hey, if my current position, so if my center right now is available, so if it's an L, right? L means available. It's L I want to do some code. Then otherwise, if center is a occupied seat or a hashtag, I'll do something else, right? And so let's finish this if statement. We'll say, hey, if our target seat is an L and the num occupied around it is 0, according to the problem, then we can actually occupy this seat, right? So what I can say is, this is the important part, for my new grid, right, I'm going to assign its I and j index to be occupied. So I'm flipping that L to a hashtag if nothing around it is also occupied. But on the flip side, if my target seat is already occupied and we'll say that the num occupied is greater than or equal to 4, then I need to flip this to be unoccupied. So I set new grid of ij to be an L over here. Nice. So this should perform the logic of flipping a seat appropriately, right? So let's go ahead and maybe just try this on our original input. So I'll just have this function maybe return my new grid like this. I'll try it on like my kind of a special input I create over here. So we'll go ahead and just go ahead and look at what happens when I console.log the next generation of the bordered grid. And we're going to look at the original as well. So we'll console.table the next generation. But I also want to look at the original, right? So I'm going to print out 2 grids and only 1 generation of it. 1 other generation, that is. So let's see what this looks like. So we're getting an error. Our row is not defined. Let's go ahead and debug this one. So it's complaining about, looks like line 29. Row was not defined. Over here, oh yeah, it's not row. I should be saying I and j, right? So let me fix these up. So I and then j over here. Cool. So with that change, let's give it a shot. Getting another error, cannot read property 1 of undefined. So that kind of tells me that we may be looking out of bounds. Yeah, and that makes sense because although we made sure to avoid iterating through the border, we want to make sure we also stop early, right? This avoids like the top. I want to also avoid the bottom border, so I can do -1 over here, right? Stop 1 more early. Then I'll do the same thing for my j, right? -1. That way I don't touch those edges at all, right? Cool. So this output's looking a lot better. If we do a quick spot check, we converted all of these open seats to taken seats, which does make sense, right? All of these L's definitely are surrounded by 0 occupied seats. Nice. Let's try the opposite scenario. So now in my example, let's say I made a bunch of these seats occupied, sort of like this. And we'll see how they sort of react, right? Let's give that a go. Nice. So yeah, this makes sense because only a few of them should actually flip. So here's my original one. Let's take a look at this particular seat at index 1, 1, right? So this is an example of a seat that did not flip, right? according to my code, a seat that is occupied is only going to become open if the number of surrounding occupied seats is greater than or equal to 4. For this particular seat, the number of neighbors that are occupied is really just 3, right? 1, 2, 3. And so that's not greater than 4, so this one stays. If we look at another scenario like this seat, we see that it actually converted to an available seat. That's because it had 4 neighbors that were occupied, right? It had this 1, 2, 3, and 4. Remember that we do want to check the diagonals. So overall, I'm pretty satisfied that this code performs the correct rule manipulation on a grid. Now we just want to make sure that we can actually execute this function as many times as we need until our grid becomes stable, which is some pretty interesting logic, right? So there are a few ways you can kind of code that up. Here's what I'll do. We have our bordered grid. Let's say we create a kind of general variable that we'll be reassigning to. So we'll say current grid equals bordered grid. Then I want to run a loop. So I'm going to say while. And in the long run, what I kind of have to say is while, my grid is like not stable, right? While not is stable, do some code. So I'm not sure how I'm going to actually create this variable or create this logic, but on a single generation, all I have to do is really just call next generation, pass in my current grid, and that should give me my new grid, right? So let's actually get that information out. So I'll say const new grid. And I'm just going to end up reassigning this back into my current grid anyway. So maybe I'll just go ahead and do that here. So I'll say current grid, right? So reassign the current grid with your new grid, which you get from next generation. Nice. And then from there, we'll just go into another iteration and keep doing that. But obviously, we need to make sure that we eventually stop doing that when there's no change. Well, we should actually maybe make the next generation function, tell us whether or not there was a change. So here's what we'll do. For this next generation function, I know a change has been made only when this if statement or this else statement has actually been executed, right? So here's what we'll do. Let me create a variable over here. So I'll say const, and I'll say is stable. I have to say let here because I'm going to reassign it actually. So when I start generating, I'm going to assume that things are stable. So I'm going to say true, right? And then by the end, I don't only want to return the new grid. So I'll return the new grid, but I also want to return the value of is stable, right? So I'm returning that information in the JavaScript object. And so imagine that I'm kind of iterating through. I start is stable to be true. And then let's say I figure that I need to flip something. That means that it's definitely not stable anymore. So I should set these variables to be false. Right, is stable false over here. Cool. So if a change is made, I set is stable to false. If no changes are made, then is stable stays as true, and I'm just going to send that in my return object as well. So now we can kind of receive that over here. We're saying that next generation returns those two things. So it returns to me, I call it the new grid. So new grid. And I also took in the is stable variable, kind of like this, right? So that should be good to go. So I have new grid and is stable. Let me actually maybe have different variable names here so we don't get too lost in the sauce. I'm going to call this one over here maybe like stable. So make the key of it stable. That way I can destructure it just by saying stable like this. Cool. So I'll call those my variables. And then I still want to reassign the current grid to be the new grid. At the same time, whatever the state of is stable is, that's going to become whatever stable is from the next generation function, right? Cool. And I need to make sure that this variable is actually created. Maybe at the start we kind of must assume that let is stable equal false, right? So if I do a quick spot check, if I begin this variable as false, then my while loop on the very first iteration says not false, which is true, so I execute the code, right? Let's say we keep going through our generations. Eventually, stable, this value I get back from next generation, this is going to be true, right? So I'm going to take that true and assign it into isTable. So at the top of the next iteration, I say not true, which is overall false, and I exit the while loop, and I should be done, right? And I have a grid that's in a stable state. Cool. So that code's looking pretty good. Let's go ahead and maybe just print out, let's say console.table, print out what our final grid looks like after it stabilizes. So I'll print out my current grid at the very end. And why don't we just try it on this kind of very small example. I'm going to turn it back to a bunch of L, so it's LLL, something like this before, right? So let's see what we get. And we'll run node part1. Cool, so this looks like a stable state. And I'm guessing even on our large input, if I change this to, let's say, our input file, that's a huge one, I should also get a nice stable grid, although it doesn't really format well because it's really, really huge. I'm going to assume that it works, right? To actually test our code and figure out and compare it against this answer, remember that we want to find the count of all of the occupied seats after it stabilizes. So let's just go ahead and hammer out that logic. So to me, this is a pretty straightforward just character counting problem. Just want to basically maybe check things within my grid. So I'll say const, we'll say, I don't know, char count for a grid. And nothing fancy here. I'll just go ahead and use nested loops, maybe the same loops as before. That should be okay. I'm going to just count the number of a target character that I see. So I'm going to assume I take in some character here. I'm going to check, hey, if the thing I'm iterating through, so if grid at index I, j, if that is equal to my character, then things are good to go. So I'm going to increase a count, right? So I'll say let count over here. Now I'll increment this. So count plus equals 1. I'm sure there's some typo here, but we'll just run and debug it together. Something I'm also noticing is I do believe that in this problem on Advents of Code, they're assuming that you always get a square grid. But let's say that was not always certain. Then I guess I should say in these expressions, look at the inner width of that just to be super safe. But apparently it didn't really cause any errors. So now that I have the char count, what I really want to do is return, we'll say over here, return the char count of the current grid for occupied seats, so for hashtags, right? How many hashtags are inside of that final grid? So I think we're ready to give this one a shot now. If things are working, we should get the result 2324. So we'll give it a go. Nice, and there we have it. It was quite a bit of code though. So nothing too complex really, just a lot of maybe neighbor checking, as well as making sure that we don't do any invalid checking outside of valid indices of our grid array, right? But with that, let's go ahead and talk about part 2. It's a lot more interesting, so let's hop to the whiteboard. So in part 2, we want to adjust our rules a little bit. For point 2, instead of saying that full seats become open if they are greater than or equal to 4 full seats, we're going to increase that to 5 now. And along with that, we're going to kind of change the definition of what it means to look at our neighboring seats around us. So it's going to be much more complicated. So from part 1, it was pretty clear that to consider all of the neighboring seats around some target seat, all we had to do was look at the immediate 8 neighbors, right? Directly up, down, left, right, and also diagonal from our current location. However, now we don't just want to consider the immediate neighboring seats. It's going to be a lot more interesting. So let's step through an example. Let's say I had this grid. And let's say I was targeting this particular seat. If you wanted to figure out what are the neighboring seats around this one, well, now you actually look along all 8 of your axes, right? So I have the vertical one, the horizontal one, and both diagonal axes. And basically, your neighboring seat around you would be considered anything that you intersect with when you look at these axes. And more importantly, it would actually be about the first seat in this kind of line of sight, right? So if you think of each of these yellow lines as a line of sight, a neighboring seat would be considered the first one that you run into when you look in that direction. So for example, take a moment to look at this and count the number of red seats that are in my line of sight and also the number of green seats that are in my line of sight. So I'll mark them here. So for my full seats in my line of sight, I have them marked with an X. Then all of my open seats in the line of sight, I have marked with a green check mark. And so here I have overall, I have 4 full seats around me and also 2 open seats around me. We have a very interesting scenario over on this side, right? Look at what happened here. So we see that, hey, this green seat and red seat are, right next to each other, but relative from my target position, I would actually consider the green one as my neighboring seat around me. Right, and that's because it appears first, right? If I would look in that direction, I would see only the green one and not the red one. And so this one's going to be pretty interesting to code up. Not only do we want to look in, all 8 directions, but we also really want to target the first seat that appears in that direction. If you're familiar with chess, this is very similar to how like a queen moves on the board. So I think I'll implement that in somewhat of a similar way, right? It looks like I have a vertical axis, a horizontal axis, and both diagonal axes. And in the long run, we still want to run basically the same overall logic as before. We want to keep evolving the grid until we converge to some stable state, after which we'll count the number of red or full seats. I think with that, we should just really hop into coding this one because I think it's going to be quite a bit of code. So for part 2, I think we'll actually just walk through my solution together. I have it already coded out. It's really more tedious than anything to actually write, although the logic that we want to establish is exactly the one that we sketched out on the whiteboard. So to solve part 2, I have it pre-prepared over here. Really, a lot of the work was about creating those methods to get all of the elements on the same axes, right? So I called them my x-axis, that means going across, my y-axis going down. Then I also have a z-axis, and what that does is give me the diagonal from top left to bottom right. And then finally, my get w, which gives me the opposite diagonal, right? Starting on the top right and going to bottom left. So a method like get x is pretty straightforward. Although what I did was also reverse the kind of halves of the array to make sure that my nearest neighbor, my nearest neighboring seat, would be at the front of the array. So here's a quick example of that. Let's say that I called getX on this grid that I have as an example, right? Just some numbers inside. That way it's easy to tell what kind of elements we're looking at, right? And where the pattern's at. So let's say I passed in this grid, call it grid 1 over here. And let's say that right now I want to find everyone on the axis of this 15, right? So what should that look like? That should be 0, 1, 2. So 2, 2 is the index of that one, right? So let's see what we get. Console.log this. So what do I actually give back for this x-axis? You might notice that I actually give back 2 subarrays inside of a larger array. So we'll run part 2. We'll just pay attention to this first array, right? So bear in mind that I basically have my target as 15, and I want the x-axis, so that means a row, right? So here, I put everything to the left of the 15, which is the 13 and 14, but notice how I ordered them, right? I put the closer elements at the front of the array, so it goes 14, then 13. Then on the flip side, everything to the right of the 15, that is the 16, 17, and 18, I have them separate over here, but it's still the case that the closer elements to my target, which was the 15, appear first in their subarrays. So that's a really important pattern to make sure that we can focus in on the nearest thing in that line of sight, right? So getX is pretty straightforward. Let's say now I kind of flip that around and I did a getY. You'll see that's more or less the same. Not only will I print out that thing, but let me also maybe print out the grid. So I'll say console.table of that grid 1. So let's see both of those pieces of information. Cool, so here we're targeting the 15, but now we're looking at that vertical axis. So I have 9, 3, right? Notice that 9 is at the front because it's closer. And then also the 21, 27, and 33 in a similar way. So getting the horizontal and vertical axes is not very interesting, but getting the diagonals is definitely a lot more tedious to do. So here's my code for getting the z-axis. So that gives me the diagonal from the top left to the bottom right. Let's see how this one works. So let me test this getZ function on that grid. We'll see what we get. So again, we're still targeting the 15. Notice that I am getting the diagonal, right? 8 and 1. And I also get the diagonal coming afterwards, right? So 22, 28, 36, still following the convention that my nearer neighbors always appear at the front of that subarray. And finally, the get W is very similar, just figuring out the math for the opposite direction, right? So get W over here. Really just a matter of some tricky arithmetic, right? So for get W, we're still starting at 15, 15. Notice how these elements are split up, right? 20, 25. Again, closer one comes first. And then in the other direction, it's 10 and 5, right? Cool. Get W is very similar to get Z. It's just a matter of different arithmetic, right? So let's say I was at the 15. If I wanted to get like my neighbor to the left, what I do is subtract my column by 1, but increase my row by 1, right? Or I subtract my column by 2 and increase my row by 2. And that's why I have this kind of syntax over here, where I add to the row but subtract from the column. And to get it on the other side, you kind of just flip that around. You subtract from the row and then add to the column, right? So this code is looking pretty good, and it's already working, but just go ahead and see that. The answer here should be 2068. So using those methods, how does my main function actually change? Well, not too much. Once I actually get all of the neighbors and the logic to do that, I create a nearest neighbors function, right? So notice what it does. I create an array of all of the neighbors, and then I iterate through each of those functions, right? Using some nice kind of JavaScript functions as first-class objects style over here. And what I do is I get both of the arrays I get back, and I know that my near elements would be at the front of both of these arrays. We call them side A and side B. And then for every element, if it's not a dot, then it's a neighbor that's either a L, so an unoccupied chair, or it's a hashtag meaning an occupied chair, right? And once I actually find something that is at least a chair, I go ahead and push it into my neighbors array, and then I break, right? There's no points of iterating through an array further once I found the first chair, right? And I do that for both sides. And in my simulate round function, now that I get all of the nearest neighbors, then I just do a quick count, right? How many of those neighbors are occupied, and increment that variable. And then it's the same logic as before over here, right? For flipping an L to a hashtag or a hashtag to an L, but I did adjust this. It used to be greater than or equal to 4, now to greater than or equal to 5. So, and there we have it. We have it to 2065. It does take a little bit to actually run, but it does give us correct answers. I did test this on the Advents of Code. Awesome. So that's all I got for day 11, part 2, and I'll catch you tomorrow for day 12.